Host disabled participant screen sharing. Another week, another error message.
Go for it.
Okay. So today is April 24th, and we're going to configure a battery pack. So last week we were talking about battery cells, and we had these four kind of key vocab words related to the cell, so voltage, capacity, power, and energy. And we also talked about how you could calculate them or how they were defined. So voltage has units volts, capacity is amp hours or current times time. Power is watts, which is calculated by voltage times current. And energy is power times time, so voltage times current times time, or voltage times capacity. They're all the same calculation. So all cells, whether they're a pouch cell, a cylindrical cell, a big cell, a small cell, a red cell, or a blue cell, they can all be evaluated by the same metrics. So this week we're going to talk about putting cells together into a pack. So our accumulator needs to store far more energy and deliver more power than any single cell can manage. So we're going to use this hypothetical blue cell, and we're going to give it these characteristics. We're going to say it has a nominal voltage of 3.6 volts, a capacity of 3.4 amp hours, and we're going to say its max discharge current is 10 amps. So one way of connecting them, if you want to build up a battery pack, is connecting them in series. And as you connect cells in series, the voltage will increase, but the capacity will stay the same. So if you have 4 cells in series and there's only 1 cell in parallel or 0 extra cells in parallel, we're going to designate this battery pack as 4S1P. And if we wanted to calculate how much energy it could store, we take the voltage, 4.4 volts, multiply it by the capacity, 3.4 amp hours, we get 49 watt hours of energy. And if we want to see what's the maximum power this thing can put out safely, we'll look at its voltage and its current, and we'll calculate 144 watts. So those are 2 key metrics for this battery pack that we put together by connecting cells in series. If we're going to attach them in parallel, so there's still just 4 cells, as you connect them in parallel, you increase their capacity, but you don't increase their voltage. So if we're going to designate this with the abbreviation, we call it 1S4P, or one set of series cells and 4 sets of parallel cells. So we did the same energy calculation with new numbers. We have 3.6 volts times 13.6 amp hours gives us 49 watt hours, and the max power, we have 4 cells. Each one can put out 10 amps. So this battery pack can put out 40 amps. So 40 amps times 3.6 volts is 144 watts. So what's the difference? Because we just made these calculations and we decided both of them can store the same amount of energy and they can both deliver the same amount of power. And here's those 2 calculations with the numbers we just went through. But the main difference is the amount of current that both of these battery packs are using to deliver the same amount of power. So power is equal to the current times the voltage. So the series pack, the 4 cells in series, has a higher voltage. So for the same amount of power, it uses less current. So the parallel cell battery pack uses 40 amps to deliver 144 watts, and the series pack uses 10 amps to deliver 144 watts. And that's important because based off of Joule's law of heating, when you have an electrical resistance and a current, the power you lose to heating is the current squared times the resistance. So power lost or power wasted in your drivetrain is a function of the current squared times the resistance. So that means a higher voltage pack could deliver the same amount of power more efficiently. And at our first presentation 2 weeks ago, we talked about all of the different places there's resistance in the battery pack, whether that's the cell itself, the spot welded connections, the fusible links, any of our bus bars, bolted joints, components, all of those different things are carrying the pack's current. So at any one of those locations, we're going to be wasting power based on this equation, current squared times resistance. So if we can reduce current, we very quickly gain back that power through efficiency because of this squared relationship. So I just added a new hypothetical just so we can look at the numbers and go through an example. So if we had a 10-volt battery pack and it was delivering 2 amps through a 1 ohm resistor, that's 20 watts total. That's 10 volts times 2 amps. And then I squared times R, or the current squared times the resistance, means that we're losing 4 watts to heat. That means 16 watts is being transmitted as usable power. That means this battery pack is 80% efficient. If we double the voltage and therefore halve the current, we would still have 20 watts total of power in the system, but now we have 1 amp squared times 1 ohm. We're losing 1 watt to heat. We're using 19 watts for power transmission, and now our battery pack is, or this system is 95% efficient. So you very quickly can make pretty significant gains in your efficiency, which we've decided based on our previous presentations is one of the most important things you can have when designing an accumulator. So if you look at real power transmission between big generators in different cities, they're running at hundreds of kilovolts. These are hundreds of thousands of volts that they're using to transmit power, because that super, super high voltage allows power distribution to happen really, really efficiently. So these are just some examples of different sizes of power transmission lines and some examples of what voltage they run at based on their shape and kind of what they're transmitting power between. So any questions about this first section or things I should go over again before we keep going? I'll wait the uncomfortable 40 seconds.
Can you go back through the slides kind of slowly?
Yeah.
Wait, pause here. Or the, yeah.
Here?
Where does the 13.6 amp hour come from?
So
it's just adding.
13.6 is adding the capacity of every cell as you connect them in parallel.
Okay, gotcha.
Cool. So the next things to think about when you're putting your pack together, knowing those relationships and those calculations, are what are your requirements? And for our battery pack, and for basically anything you design in this fashion, it's storing a certain amount of energy and delivering a certain amount of power. Our accumulator, our high voltage battery for Mark V has a 7 kilowatt hour requirement and an 80 kilowatt power requirement. The low voltage battery has a very, very different requirement, but it can be designed using the same exact principles. There's also the design constraints. So at yesterday's mechanical presentation, this was a really important topic that we talked about. And the important idea here is there are other constraints besides the function you're looking to achieve that reduces the number of options you have. And in this case, reduces the number of configurations that are viable for building your battery pack. So when you first start this process, it can maybe be overwhelming because there's infinite numbers of combinations of series and parallel cells that might be viable. But as you think of all the different constraints, there's a peak voltage that the rules limit. Certain components in our powertrain have max voltage ratings. In this case, our motor controller is the limiting factor at 420 volts. the accumulator has to fit within a certain amount of space, and the accumulator has to be divided into a certain number of segments. So we have 6 segments in the Mark V battery pack, and the rules designate that each one can have a 120 volt max or a 1.66 kilowatt hour max for energy storage. So as you start to think about everything that constrains your design, you quickly narrow down to many, many fewer viable options. And if we have a little bit of time at the end, I'll show you some of the spreadsheets we made to help make these decisions with a lot of these constraints built into it. One note is, as of last year, the Mark IV year, the rules changed. So the max voltage the battery pack was allowed to achieve was changed to 600 volts from 300 volts, but we didn't buy a new powertrain since the 300 volt rule. So our max voltage is currently constrained to the motor controller, which is 420 volts. But one day in the future, maybe we'll buy the high voltage version of the same model if we decide that increasing the voltage has enough gain to warrant the financial cost. So let's talk about adding more than just series and parallel cells together, and this will be based on cell characteristics. So a single cell has a certain amount of energy, in this case, 3.6 volts times 3.4 amp hours gives you 12.24 watt hours. And then it's the same cell we talked about earlier. Let's say it's 10 amps max discharge, so 10 times 3.6 gives you 36 watts. And as we build up this battery pack from one cell, you can see every cell we add adds a certain amount of energy and it adds a certain amount of power capability. So at every cell, I've just calculated the voltage times the capacity to get the energy. And then at the same step, I calculated the voltage times the max current, which is 10 amps, to get the max power. So you can imagine if our requirement is 7 kilowatt hours and a certain amount of power, but we're constrained in voltage, we're going to be adding cells in series until we hit our voltage limit or our near voltage limit, and then we're going to be adding cells in parallel to add energy and power capability. Oops, that slide was a mistake. So this is what the next slide is supposed to be, but now if you have 2 series strings in parallel, you have now doubled your capacity. Capacity is now 6.8 amp hours or 6,800 milliamp hours, and the voltage still steps up the same amount at every step. So you can see all the calculations, the same ones in the previous slide, but now with this new configuration. And this kind of pattern is the same, is exactly what would happen if you added more cells in series or more cells in parallel. You're effectively increasing the amount of energy stored, increasing the voltage, increasing the capacity, and increasing the amount of power. So an important thing to note is that the way you increase power and energy is dependent on the characteristics of the battery you are using. So we looked at this graph last week, and it told us that a cell usually has a high power capability or a high energy storage. So there are lots of cells in this area where there's lots of capacity, but not a lot of current output. And there's some cells up here, less capacity, higher current output. And there's some cells kind of in this golden region where you get a good number for both. And this is where we are operating. And the ratio of these two will decide if, as you increase the number of cells, are you going to hit your energy storage number first, or are you going to hit your power number first? And whichever one you hit first is going to be in excess before you hit the other. So an example is if we were looking at this battery pack that has 2 parallel strings, and if our requirement was 73 watt hours of energy storage and 250 watts of power output, we could get to this third section if we had 2 cells in parallel and 3 cells in series. So ignore everything, ignore the last 2. That would be 73 watt hours and 216 watts. So now we have enough energy, but we can't put out enough power. And that's because as we're adding energy and power to this battery pack, we're getting energy faster than we're getting power, and that's limiting our power if we stop there. Or we could increase, and we could add 2 more cells, and now we have enough power, a little bit extra, but we really have a lot of extra energy. So a challenge that we have is picking the right cell and configuring them in the right way to get the best ratio of energy to power. Because any extra cells you have, because to get to your requirements is excess weight, which, as we talked about earlier in the mechanical presentation, is one of the big areas that you can improve the quality of your race car. So some notes in conclusion: it's important to really know the characteristics of the cell you're starting with, because everything is cumulative from that single cell as you're adding energy and adding power. Building up your pack means you need to really clearly define your requirements and understand the design constraints that you're working around. And knowing both of those will make sure that you are considering only the right options. And then every pack, no matter how you configure it, will have some pros and some cons, just because there are so many ways to evaluate it and so many considerations. So no pack is 100% perfect, but knowing the ways to evaluate your design and knowing your requirements will help you make the right decision. So I'll stop there for questions, and then I'll pull up the spreadsheet that we made this past year and maybe show kind of what that process looks like. I won't step through every calculation, but I'll link it in the channel after this. You can spend some time looking at it if you'd like to, but I'll stop here for questions. Feel free to unmute yourself and shout them out.
I have a question. So one thing, why is it called an accumulator as opposed to a battery?
I think the name accumulator just means you're accumulating energy, whereas a battery is technically a single thing.
Oh,
I think
so
it's because technically you can use capacitors or something like that. And so it's not necessarily limited to batteries. So it'd be a wrong thing to say, to call it. So we build a battery pack, but if we wanted to just use a bunch of capacitors, it'd be an accumulator.
interesting.
Yeah, that's what, because it accumulates charge.
Cool. And I'm pretty sure that the Formula car is DC, but I know some electric cars are AC. What are the advantages, disadvantages of that?
Well, every motor is powered with AC current, so the battery pack is hooked up to your motor controller, and the battery pack delivers DC current to the motor controller, and the motor controller delivers AC current to the motor. For every car that I'm aware of, every battery pack is putting out AC or DC power and uses an inverter. I've not heard of anyone or any car that does something different.
I don't even think AC batteries exist.
Yeah, not the AC battery, but like if you're using like a brushless DC motor, your motor controller it's not like a true AC. You know, it's but I think some battery packs go directly to like a alternator, and then the motor is actually an AC motor.
Yeah, you can draw AC current from a battery. I don't know anything about it though, so I can't answer that for you.
I think not very many people use brushless DC motors just because they're less efficient and you don't get as much control over using like an AC motor like we do. Because like you suggested, you're just hooking up the DC like plus and minus to the motor. There's not much you can do with that in terms of control as far as I'm aware. You can do some things, but not a whole lot. Like yeah, like I don't know. I don't think you can do. Yeah, I'll just leave it at that.
So you go from the battery to an alternator, and then the motor is an AC motor. Okay. And how do you
Yeah, the motor
control
controller is an inverter. Sorry, what was your
But-
question?
So the motor controller, like you'll send it a signal and it'll supply a certain amount of amps for output, and that'll determine your speed, or is it voltage regulated for speed?
I mean,
So the
you
motor controller gets a torque request from the pedal,
Yep.
and depending on the speed that the transmission is running at, it converts the amount of torque that you're asking for to a certain amount of power needed. And that maps back to the same equation we just talked about, power as voltage times current. So whatever voltage your battery pack is at, it draws the right amount of current to get the right amount of power to deliver the right amount of torque.
Gotcha.
This may be addressed when you're presenting the spreadsheet, but I'm wondering what difference there was between the segments of Mark IV and Mark V and why there were differences, if there were.
So
I know
the main, oh, go ahead, Katja.
I think just one of the biggest differences was that we used the same battery, but we had a different energy capacity. We had a different capacity number that we used for both years. The second year is based on not our testing, but MIT testing, whereas the first year, I'm not actually quite sure. I think we just used the data sheet or something like that. So we had
No, the first year is based off of the data that MIT sent us.
Oh, and the second year was based off.
And the second year was based off of different testing that we found online that's more consistent with the predicted calculation. We also increased our voltage between Mark IV and Mark V, just because it was convenient it was convenient based on how much energy we needed and what size we were playing with, and just the constraints we were working with this year.
When you have such high voltage packs, like 300 plus volts, or do you run into a big issue with voltage drop of the batteries? Because I mean, if it's 3.6 nominal, like 4.1 max to down to, well, I don't know what exactly the usable range is, but you're going to get a big decrease in voltage from the top to the bottom. Do you have to deal with that at all?
Yeah, so the minimum is 2.5, and it drops off really drastically at the final percentage of the battery's life, like the end of its state of charge. So we intentionally design to store extra energy so that the range that we're using the battery pack is more constant, and we don't use the battery pack in the final region of its life where the drop off of voltage is really significant. So based on our simulation, we're running it from around 4.2 volts to 2.9, as opposed to 4.2 to 2.5. That was a question I also had this summer when I asked someone at work why most like commercial cars run around 300 to 400 volts, because they obviously don't have the same rules that we have. And he said that the reason you stated was a big reason. So like if you get up to like 800, 900 volts, then your swing between your peak and your minimum is like a couple hundred volts. So if you have to design for the low end of your swing, then you don't get as much benefit in terms of lighter weight components or significantly greater efficiency. So that was kind of the reasoning that he gave for why commercial vehicles aren't at super high voltages. Another thing worth mentioning is these topics are another reason that we use cylindrical cells versus pouch cells, because a cylindrical cell is much smaller and has a lot less capacity than a pouch cell. It means we can configure the pack a lot more creatively because we have a lot more room to design different options to get to the same result. Whereas a pouch cell, because it's so big and has so much capacity, we can only wire them basically in one or two different ways, which might not be optimal based on how the vehicle is laid out or the chassis is being designed that year.
But just the reason for why we were using pouch cells before is just because when you have a lot less cells, it's a lot easier. It's a lot less repeatability when it comes to manufacturing, and they're a lot more safe. They're a lot safer, in case you guys were wondering.
Yeah, most like commercial vehicles that care about how fast it is to build a pack use pouch cells or prismatic cells for exactly the reason Kasha just said. Cool. Well, feel free to jump back to this presentation if questions come up. Let me switch tabs. You guys can still see my screen, right? Oh God, I clicked annotate. Uh-oh. Okay, we're in a bit of a pickle where I cannot change tabs because it thinks I want to annotate.
You can do Control Tab or Control Shift Tab to switch tabs.
Nice. Veteran move, Corey. Okay, so this is a spreadsheet. This one that Katya made. Katya, do you want to talk about it?
Sure. So it kind of goes through a similar mindset that Anil just presented, where basically we have our requirements. So as Anil said, if you look at the top left, ooh, I can annotate. This is exciting. So over here, we're basically looking at our pack requirements. So we can, based on our motor, we can only go up to motor controller, we can only get up to 420. And then basically there's a bottom minimum desired voltage, which is basically reaching up the limits, but gives us more choices depending on how the configuration might go. And then we need at least 7 kilowatt hours of capacity, and then our peak powers. And basically what it does is it takes the cell specifications and figures out the limiting factor when we add them up into for series and parallel, and sees whether we're limited by our power or by our capacity. So that's what it's doing right here. So so right here, it's the number of cells to reach the capacity we need. Can you guys see my annotated? Because it keeps disappearing. Okay. Okay. I don't know if I'm annotating.
Yeah, I see them.
Okay. Well, they're all gone for me. So basically the number of cells we reach capacity is here. The number of cells we needed to reach power is there. As we can see, we need more cells to reach capacity. So we're limited by that. So we need that number of cells. And it basically splits them then up into those segments that Anil was talking about that are required by the rules. So you can only have a certain amount. Each of your segments is separated by weight, energy, and voltage. So it takes the amount that we need for the peak, for what our pack minimum requires needs to be, and separates those. And takes like all of these is basically like, if you divide it into segments and it's like 0.7 or something, it will always take the maximum of the cells. So you figure out the cells in series and cells in parallel, and you get a certain amount of range. And so down here, that's figuring out, oh, thank you. That's figuring out the number of cells segments and the number of cells in series to figure out how many segments we'll need. So basically in order, we have our 9 cells in parallel and our number of cells in series on the left. And it tells you the amount of segments you need. And the cells in green are basically the most viable segments to look at because it's a smaller amount of segments. So that just means that you need less materials to build those segments and it will be easier to manage. You want less segments because with more segments, that's just increasing the number of connections between each of the segments and the number of barriers in your enclosure. And if we go into the segment in packing parameters, this is basically looking at, okay, like comparing the two segments, like we're comparing the capacity of the pack, the voltage of the pack, and seeing and looking also at like some estimates of the sizes of the segments to figure out what we want more. And the one in light green or neon green is the one we chose with. One of the main reasons is that it is a small number of segments, and it has and it has also it has one of the higher pack capacities for the number of segments it has, while not oversizing by too much. Does that make sense?
Just to clarify, is the weight requirement for cells only or for the entire segment itself?
It's for the entire segment. So usually we're not actually limited that much by our segment weight when choosing our pack configuration. So I think if you scroll up, yeah, so if you scroll up, it's not even really, I don't even think I chose it. 12 kilograms is so high compared to what our segments weigh that it wasn't, I guess I didn't even put it as a factor in terms of figuring it out to make sure that we're not over it. Yeah.
What's the total number of cells with 8 cells in where the red arrow is right now?
Oh, so it's, I don't know what the total number with 8 cells is, but I think, so basically once we figured out the amount, so, okay. If you look here in my annotation, basically in order to get the max voltage that we need a certain amount of cells in parallel and so to get the max voltage. And so to like look at a couple different configurations with the based on the max desired and the minimum desired voltages, we need at least 9 cells in parallel and 10 cells in parallel. And so that's looking at them in basically if we like, can you scroll down, please? So that's what we're examining in here in these two. So if we have those 9 cells and 10 cells in parallel, and then the number of cells in series to accommodate those cells, and that's how we can figure out what our segments need to be. And that's what these are right here.
And then are the numbers like up top, the really large numbers, the total number of cells that we would
Those
need?
are the total number of cells. And so these are the total number of cells. And then if you look at the ones behind it, underneath it, that's the number of cells in series.
Okay.
It is a little confusing. And to be quite honest, I explained it really poorly. So I'm sorry about that.
This is a really cool spreadsheet.
Thanks. Any other questions?
Is this spreadsheet what you use for like final design, or do you guys kind of like, this gives you a rough idea of what the design should be, and then you guys play around with it afterwards?
So if you see like the segment and packaging parameters, what kind of happens there, and there were some more characteristics, but these are basically like the segments that are probably viable for what we want. And then we kind of look, we kind of then look at how we could package them. We kind of take the best 3 or 4 or 5 and kind of look at how we could package them, and see how much space they might take in the car. So we then like use SolidWorks and basically just try to figure out the dimensions of our pack, how they might be. And that's kind of how we decide between the top 3 or top 4. There's also, Anil did this in his cell configuration, but looked more at like, okay, comparing current drop of each of the cells, so that we could see how efficient they would be, and how much power we might be losing to heat. So that's kind of like the top contenders between how we chose our segments, or how we chose our pack configuration.
Yeah, I'd say the packaging numbers are definitely the most iterative numbers, just because all the pieces between the cells and like the box and the segments are the things that are a bit variable. So these numbers are somewhat of an estimate. When you go to CAD, figure it out, talk to the suspension, see if it's possible, talk to the drivetrain, see if we're going to fit. So packaging things and laying things out are a lot more variable between evaluating these and getting to a final solution. The better you communicate with the other teams and the earlier you can have good answers about these, the more likely you are to be able to use the configuration that's best for us on the accumulator team. That was definitely an issue we had with Mark IV that we did a lot better with Mark V in terms of communication. But if we did all of this kind of in isolation and said, okay, the highlighted green one's the best, we might go to suspension and chassis, and they might say, well, we don't have space for that. We might have to pick one of the less favorable configurations, or lessen our ability to hit our requirements because we didn't communicate very well.